Yeah, so if I want to give a quick overview of my research, is basically in the health domain is I use three ingredients of passive sensing, longitudinal data collection, and behavior modeling to detect and predict an outcome, a health outcome to provide interventions. So most of my work has been in the domain of physical and mental health, like detecting depression, loneliness, episodes in bipolar disorder, sleep quality, etc. But today I would be focusing on hospital readmission risk, partially because it is relevant to the topic of this workshop on deep learning and health, and partially because it was kind of a different problem that we had to solve. So this work I did with Anende and Carissa Lowe at the University of Pittsburgh. So we started working on this when both Anand and I were at CMU. Now he's at the University of Washington, and I'm at Virginia. Carissa Lowe is a clinical psychologist who we collaborated with, and we got, she works on cancer patients, and that's how we got the data. So we did not know much about hospital readmission, but we got some information. So actually, hospital readmissions are very common after surgery, and they're costly. Up to 50% of patients experience unplanned readmission after surgery within 30 days of discharge. And these readmissions cost the US healthcare system billions of dollars, and it also is a source of suffering and stress for patients and their family. But the good news is that hospital readmissions are preventable. So up to 82% of cancer patients' readmissions can be prevented. If we can accurately predict the readmission risk early, then we can avoid a lot of these cases of readmission. However, it is challenging to predict who will be readmitted to the hospital following surgery, because there are traditional methods to measure the risk of readmission in patients based on their demographic and medical history, but all of them classify all patients almost at high risk. And there is no existing method to measure daily risk of readmission to know who will be in risk of being readmitted to the hospital. So our question was, can we predict daily readmission risk at all? So we know that daily behavior and activities may signal or contribute to increased or decreased risk of readmission, depending on what patients do, like they're active or not, and so on. And if we can monitor their daily behavior after their discharge from the hospital, of course, using smartphone and wearable devices that are now available, we will be able to model their behavior using their movement patterns, social communications, heart rate, quality of sleep, and then understand if there is any associations between the readmission risk and so on. So mobile and wearable technology have been used to predict readmission. We only are aware of a few studies on, actually, there are my colleagues and my own group have done that. My colleagues showed that low activity and sedentary behavior after surgery contributes to early readmission. I also presented a paper at UBCOM last year showing that disruption in biobehavioral rhythms during treatment would predict readmission. But none of these studies actually modeled and measured daily risk of readmission. So Our question was how to predict readmission risk. Can we at all do that? So we built a probabilistic framework using a LSTM structure to infer the trajectory of risk in each patient from their behavioral models that we extracted from mobile data. So there were several steps in this framework, starting from processing the data, of course, that most of you are familiar with. You know, like there's feature extractions, handling missing value, normalization of the data. We have developed over the years as we have worked on this mobile data processing, mobile and wearable data processing. We have developed a framework for feature extraction. We extract tons of features from this from different sensors, including statistical features like mean, max, standard deviation of a certain feature in certain time window. It can be daily, can be hourly, depending on what we are interested in. Behavioral features like more related to movement patterns, for example, how often the person moves, how often they go out, and you know, like how well they sleep, etc. We also extracted some what we call deviation features, where we looked at the difference between these the current day features and the 7 days average of the 7 days prior 7 days to this date. And we handled missing values, which is basically instead of trying to impute the data, even though we have a lot of missing values, but because we didn't know how different each patient's data was, we decided to just remove features that were missing more than 80% of the time, and remove features that did not have enough variation, and then imputed the rest with the data from prior days. And then the next step, that was a very important step, was calculating actual daily risks. Because if you wanted to know what the risk of the readmission on a particular day is, we had to know, and we wanted to predict that, right? We had to know what the actual daily risk was on that particular day. And this data we didn't even have, you know, like we could calculate it, but we didn't have it readily. And we couldn't ask patients to give us because they didn't know that either. So what we did was a set of different strategies. So what we knew was that we know the day of discharge of the patient, and we know what day they are readmitted. So assuming that on the day of the readmission, the risk probability would be 1. And also looking at the 60 days after discharge, because hospitals, if the patient is not readmitted within 60 days, the risk is almost 0. So we assume that too. But then the day that the patient is discharged from hospital, there is an initial risk probability that we don't know, but we can possibly calculate it. And then it becomes the days between discharge and readmission that our daily risk probability. These we don't know either, and we have to calculate them. So what we did, in order to calculate the initial probability, we utilized 2 existing baseline measures that are used by hospital administration to calculate the readmission risk at the time the patient is discharged from hospitals. And they're called LACE and hospital. LACE is based on the length of stay in the hospital, acuity of admission, comorbidities, and emergency room visits. And hospitals also, like different factors, hemoglobin level, sodium level, and admissions, etc. And they have different scores from 0 to 19 for LACE, 0 to 15 for hospital. So we decided to use these and get the scores, the initial scores that patients had, to calculate what we call the initial risk probability. And we use three different functions, linear, exponential, and logarithmic functions to calculate these initial and final probabilities. So we had two cases for those patients who were not readmitted to the hospital. The daily probability would decrease from the initial probability, right? Because they would not be readmitted to the hospital. And the opposite was for readmitted patients, where they, at the discharge and on a day-to-day of until they were readmitted, the risk will increase to 1. And once they are readmitted to the hospital and then they're discharged again, the daily probability again decreases from the current probability. So this is what we assumed and used to calculate the actual daily risks. So an example is, for example, let's say that the patient has a LACE index of 8, so the initial risk of readmission would be 0.4218 divided by 19, which is the highest score of LACE. And if the patient is readmitted on day 20, the risk of readmission is 1 on day 20, and every day is the risk is accumulated, you know, like based on is increased until it reaches 1, and based on the initial risk plus NP, where P is 1 minus initial probability divided by 20. So we calculated and we considered different cases where we you know, considered the maximum scores for hospital and LACE, and also we looked at our own sample population, how much their scores were, and we calculated the probability. We also took the average of the both LACE and hospital. Then we calculated the daily probabilities and then also probabilities after readmission. And then we use this in to predict the daily risk using LSTM. So this framework, and you know, in LSTM, what we did was that for each patient, we took all the features on a day-to-day basis and we used the day 1, for example, a patient fed it into the model, and we basically calculated the day 1 probability, and then fed it back to next day, fed it forward to the next day, and also it continued until day n, or until the end of day, which is 60 days of data for each patient. And then we used that became the for that we did for each patient. And then for evaluation, we did it so we use other patients' data to build, again, to refine this model. And we used it for testing. This is what we often call, or you know, usually for classic methods, we call leave one patient out cross validation. In this case, we used also other patients' data. We built the model, and each patient contributed to the refining of the model. And then the obtained model was tested on the last patient that was left out. So using this method, we would obtain two basically time series models. One was the actual probability on a day-to-day level. One was predicted probabilities. And in order to measure the performance, we needed to compare how close these two time series are, right? So the ideal model would be where the actual and predicted were very close to each other and they follow the same trend. So we incorporated we looked at different metrics, including residual, which is, you know, like the residual of the actual and probability scores, the mean square error, covariance of the two time series, and mean absolute error. And we also use different type ranking, looking at each metric alone and also a combination of them. Here, for example, what we had was for residual, we could, like we would look at for class 1, which is the readmitted patients, the smallest to largest residual would be the smallest residual would be what is most wanted. But for class 0, we rather wanted to have the predicted probability be lower than actual, right? Because because that would mean because non-readmitted patients were never admitted to the hospital, so their probability of readmission was lower. So we rather wanted to have the residual to be larger. So that's how we ranked it. And looked at also MSE covariance and so on. And then, so we did test this model on 53 patients that we had in our sample that had, like they came out of, or they were undergoing pancreatic cancer, and 34% of them were readmitted within 60 days of discharge. We collected data from a Wear device on smartphones, and patients also reported some symptoms of depression, fatigue, etc. on a daily basis. For the ground truth, we looked at their electronic medical records, where we reviewed whether or not they were readmitted and on which day. So initial results that we looked at, one was using the actual probability from previous step. So we would, like that was one of the reasons that we use LSTM, because we could use the probability from the previous step. And if we could use if we fed the actual, the probability of risk probability from the previous day, we could obtain models, using different settings that were quite similar. So here is, for example, like this is the overall average of each day from day 0 to day 60, or day 1 to day 60, of both patients readmitted and not readmitted patients. This is for readmitted patients, and this is class 0, which is non-readmitted patients. And they are pretty close. The trends are close. So we had tons of models and different combinations that we tested. So some, many of them were close. But what we wanted to, what we also wanted to look at was whether we could, or how well we could actually predict this using the predicted probability from previous steps. So assuming that we don't know anything about, like what the risk is actually for a patient, and the only thing that we get from the model is a predicted probability. How well can that, and if we incorporate that predicted probability as and feed it to the next step, how well we can predict that. So what we see is that, of course, the results are much lower, but so there are different functions and different models that are working better than others. For example, one model that we're using, as I said, we were interested in having a lower predicted probability for class 0 patient, non-readmitted patients than the actual, and this one would give us that. And if you look at this until sort of day 20, 21, this is basically the trend that we see. Looking at our data, most of the patients were readmitted within this 20, in our sample, within 20 or within 3 weeks of discharge. So probably, you know, like this, the later data is kind of, it's because we did not have enough readmitted cases, and so. But so this is basically still work in progress. We are still working on it to see how we can improve the predictions of this of daily risk using the predicted probability. So yeah, this is basically where we are at the moment, and yeah, and just with this, I just wanted to thank the collaborators and also the Health Data Alliance in Pittsburgh that funded the project.